To introduce Sophia Economou, who is a professor of physics at Virginia Tech. And she's also the Hessinger Senior Fellow of Physics at Virginia Tech. She's a valued member of our C2QA center, and her research focuses on theoretical quantum information science, focusing on topics that include quantum computing, quantum communications, and quantum simulation algorithms. So it looks like she's got a very exciting talk to tell us about. The title of her talk is Variational Quantum Algorithms. So one thing I'll say before I pass the floor over to Sophia is that we ask that, we're eager to, of course, receive questions from the audience. We ask that you please enter them into the chat window, and I'll do my best to moderate and to pass those questions along in a timely fashion. Okay, so let's pass it on to Sophia.
Great. Thanks a lot, Peter, for the introduction. And thank you for coming. So today I tried to give a little bit of a broader background on variational quantum algorithms, and then talk about the work from my group. So the main motivation for variational quantum algorithms is quantum simulation. And this is actually an old idea. It's something that Feynman suggested in the early 80s. And of course, we all know that it is difficult to simulate quantum systems on a classical computer because of the way the Hilbert space grows. It grows exponentially with a number of quantum qubits or spins or whatever your system to be simulated is. So this is an inefficient thing to store in a classical computer. And of course, there's many approximate techniques classically on how to do this, but it's actually still difficult to capture truly many body correlated effects. There's also, of course, models people use, but there's no exact way to do such a simulation. So the idea is to use quantum systems, which have the advantage that they can actually naturally have the same behavior. They do encode exponentially large Hilbert space themselves, so you can use them to simulate other quantum systems in principle. And there's two ways you can think of quantum simulation. You can think of the analog version, which is to basically recreate the Hamiltonian of the system you're interested in on a different system. And you'd probably call that a simulator or an emulator. And you can think of atomic lattices as such a system. And in this case, of course, you want the simulator to have something more than your original system. Presumably, it's more controllable. The parameters are more tunable. You can study it in various regimes. You can extract, do measurements and extract quantities of interest more easily. But of course, there's a limitation on this approach, which is you are limited by the native interactions and Hamiltonian of the simulator. And if you want to study a different Hamiltonian, then you have to go and change the physics of your simulator. On the other hand, there's the idea of digital quantum simulation, where, this is like quantum computing, where everything is decomposed in a small set of elementary gates, such as single qubit gates and C-nodes. And then in principle, any problem can be solved with a given algorithm. And the most, so before I go into details of the algorithms, let me just make this connection. There's a system to be simulated. Usually this is an electronic system, some sort of fermions, such as electrons. They're indistinguishable. You map these to qubits, which are distinguishable. I'll talk about that in some detail. You have to keep a relevant space. Some states make a choice about the states you're keeping in your original system. And then you have some Hamiltonian, which we typically write in second quantization. I'll talk about this later. And on the quantum computer side, you are creating a Hamiltonian based on this left-hand side, which is basically a weighted sum of Pauli strings. And I'll come back to this. So the most well-known approach for quantum simulation is phase estimation algorithm. And here the idea is we want to find the eigenenergy of a many-body state. And you can think of the Hamiltonian written this way. These are non-commuting terms. So I've grouped the Hamiltonian into different non-commuting terms. And we assume we have n qubits to encode this eigenstate. And there are also some ancilla qubits that we use to run this algorithm. And then what we want to do is we want to conditionally apply this time evolution. Sorry, this is a typo here. This is just these three dots should not be here. I don't know how they were left over. So this is just the exponentiation of the Hamiltonian. So you want to apply this u conditionally on the ancilla. And if you're familiar with Deutsch's algorithm, this is the same trick. You're kicking back the phase to this ancilla system. So because you're inputting here an eigenstate of the Hamiltonian, which is another unfortunate thing here is that H here is a Hadamard gate. And unfortunately, I use the same symbol for the Hamiltonian. I apologize for that. I should have noticed it. But yeah, this H is a different thing. It's the Hadamards that you do on this single ancilla considered here. You put the ancilla in a superposition of 0 and 1, and then you do this conditional U, which is just this exponentiated Hamiltonian. And then, of course, this phase is kicked back onto the ancilla. So then by making measurements on the ancilla, I can deduce this energy E. And I can repeat this in different ways so that I can get all the important decimal points of E. There's many variations. I'm not going to go into the details of phase estimation. So one challenge here is that because H is a multi-qubit Hamiltonian, so it has these different terms, what I need to do is I need to worry about decomposing this operator into elementary gates. So I need to actually trotterize this U in terms of these non-commuting H sub j's. And of course, the problem is that this is an approximate expression unless n goes to infinity. And there's a lot of work, including by members of our center, on how to make the trotterization part more accurate. But you can see here that at least at finite order, this is a problem. So you need very good quantum computers in order to be able to do a deep enough circuit to approximate this U well. And of course, this is something we cannot do right now, and we can probably not do it in the next few years. So because of that, the phase estimation is considered to be too demanding for our existing and near future capabilities. And what we want to do in the meantime is ask and answer the question, is there something we can do in terms of quantum simulation that's useful before we have fault-tolerant quantum computers? And a famous way people have proposed doing this and have done it for proof of principle examples is the variational quantum eigensolver. The first paper introducing the idea of VQE and also demonstrating it on photonic hardware actually was a collaboration between the experimental group of Jeremy O'Brien and the theoretical group of Alana Spurguzek. And the idea is exactly based on the variational principle of quantum mechanics, which is something that, of course, is taught at the undergraduate level. And it tells you that if you have some parameterized wave function, then for any value of these parameters, if you look at the mean value of the Hamiltonian, that will be smaller or equal to the ground state energy. So you can never go below the ground state energy, which means that by changing either or both the form of the variational ansatz and the parameters, you can hopefully go close to the ground state and find that energy, which is the goal you had. And this is a very simple undergraduate thing. I recently found my notebooks from undergrad, which was in Greece, and you can see it's just a 2-line proof over here to show that the variational principle holds. So it's a very simple, very simple idea. So this is the overview of how we would do this on the hardware. Of course, variational algorithm is something people look in the classical setting as well. But what we gain by doing it on the quantum setting is that we use the quantum computer to do what is difficult for the classical computer to do. And that is to store the state and, of course, to measure it. So since the quantum computer should be good at storing the state, at least for reasonable coherence times, we can create the state we want on the hardware. And we have parameterized the state with some theta here. So theta is written as a vector, but it's really just a set of parameters. So that's what that vector represents. And of course, you can view that C of theta as having some unitary t of theta also acting on a reference state. And how you choose these is kind of the focus of my talk later. And then you make the measurements also on your quantum processor. So here I measure the mean value of this Hamiltonian with respect to a state that's parameterized by theta. So of course this will depend on theta, and it will also depend on the form of this psi, which is to say the form of this t. And then you feed this information into the classical computer, you make measurements, you vary theta, and then you optimize over theta, such that hopefully you reach at least close to the ground state energy. And maybe I should mention on the slide that there's also ways people have suggested and also demonstrated finding excited states. So there's a way you can modify this algorithm to make it work for excited states. So more broadly, you could ask, why do we bother thinking about VQAs? As I already mentioned, the main motivation for this is to ask and answer the question of what can be achieved with NISQ devices. And specifically, can we reach quantum advantage for some problem that's of interest and not a made-up problem? Meaning a problem that people have been trying to solve in some other domain. And the chemistry is a prime example of that. And a lot of the examples I'll show you focus on chemistry. Another thing you can think about variational quantum algorithms is, can we get useful primitives? So can we get a piece of a circuit that does something that we're interested in a better way than we would have designed it to do that same thing? And then we can also ask more fundamental questions about what's the structure, features, capabilities of parameterized quantum circuits. Many people are working on quantum machine learning type problems and to worry about these questions. And that's something I'm not going to talk about at all in this talk, but it is an active area of research as well. So here's the outline of my talk. I did already motivate VQAs. I'll talk a little bit more about them just to orient the audience. And then I'll go on to talk about fermionic many-body problems, and specifically our work, which is focused on problem-tailored algorithms. If I have time, I'll talk a little bit about QAA and optimization, and I'll leave you with some outlook and conclusions. So there's three important pieces in any variational quantum algorithm. One is the objective function. And this includes whatever operator you're interested in, the Hamiltonian in most of the cases I'll be talking about, as well as the ansatz itself, because this is the mean value that I showed you in the earlier slide. Then there's the measurement step, and that in itself is a non-obvious step. And then the optimization also has its own challenges. Many different considerations can enter here, such as what optimizer you use and how the choice of your objective function affects optimization. So what you want from an objective or cost function is articulated very nice in this recent review paper. So they point out 4 different desiderata. One is that it better contain the solution. Sometimes we call this exactness. They call it to be faithful. It has to be measurable. This is a not very obvious thing that as you get lower outcomes for this measurement, you approach the solution more. I don't think this is an obvious thing, but in general, you would probably want it. And then you want it to be trainable. I'll touch upon this a little bit. All right, so again, I'm just repeating here. If A is H, then this is just the mean value of the energy. And as I mentioned, this depends, of course, on the observable, the Hamiltonian, if A is H, and of course, on the ansatz, how you parameterize that state and how you choose the form of the circuit that constructs it. And I'll come back to the question of the ansatz. That'll be the meat of my talk in some depth. But first, I want to show a little bit of discussion on the other parts of the VQAs. So one thing is the measurement. I will not show you any results on this, but I just want to give a feel for this. So as I already mentioned, the Hamiltonian is now represented as a weighted sum of Pauli strings. So you can group those Pauli strings in commuting sets. And then, of course, you only need state preparation for each set, because you can measure the commuting ones simultaneously. But still, how to separate them out in these commuting sets is a very non-obvious and non-trivial problem. People have suggested different things. One thing you can do is be very restrictive and make these be qubit-wise commuting. You can do better in terms of number of measurements if these are commuting but not qubit-wise commuting, so more general approach. And there's a nice paper that I'm not going to give too many details about, but basically just show you the highlights. The idea is that even though the problem is, the full problem is NP hard, of grouping these Paulis in a way that you get minimize the number of measurements, there's still heuristics you can do, and this is a very nice paper where they do that, and they show how you would want to separate out these Paulis such that you minimize this number of shots, the total number of shots. Then, of course, after you make a measurement, you also want to update your parameters, so you have to have a way to calculate the gradient. And what is nice is that if you use Pauli's or slight generalization of Pauli operators, so these are just exponentiated Pauli operators, then taking the derivative of this mean value, which is basically your objective function here. So this would be the Hamiltonian if you're measuring energy. And this would be the operator you're applying with this parameter theta at any given step of your algorithm. So if you take a derivative of this, what is nice is that you can get an exact form, which just is the same function f, which is this, just evaluated at a different value of theta. And this is exact, it looks like a finite difference, but it's not, it's actually an exact expression. So you can actually measure gradients on the hardware. There's a lot of work on this, both from quantum machine learning community and other people. So I have references here if people are interested. And then, of course, there's the optimization step where you collect your measurement data and then you want to update your parameters. And here there's challenges associated with the measurement cost. Noise makes things even worse because you might be optimizing in the presence of noise and not be optimizing the way you think you are. And then there's this problem of local minima and also barren plateaus that I'll touch upon right now. This is a figure from the early IBM paper where they demonstrated the simulation of a few small molecules. And here you see how with iteration in the optimization step, they go closer and closer to the ground state energy. So the issue of barren plateaus has to do with the fact that the cost function can have gradients that vanish exponentially as the size of the system grows. And this was something that was realized several years ago. And it is related to having too much expressibility in your ansatz. So this is probably the first indication, at least in my talk, that you don't want to have a too random an ansatz, because if your ansatz is too random, then it has too much expressibility. And it turns out that in such a case, your parameter landscape, it's very flat and hard to optimize. There's been a lot of work recently on this barren plateau problem, especially from the Los Alamos group. So I have here some references for people who want to look at that. So there was also an interesting paper about a year ago now that showed that you can possibly overcome this issue by enforcing more structure in your algorithm, and specifically this layer-wise learning. So instead of putting the full circuit and optimizing it at once, what they did here is they optimized it in layers so that the early parameters were fixed from the early optimization, and then the second set of parameters was optimized with these early ones fixed, etc. And that showed, they showed that this seems to help. All right, so this kind of concludes the general introduction. If there's any pressing questions, I can answer them now. Otherwise, I'll move to the main part of my talk, which is fermionic many-body problems. All right, so I think there's no questions, and I'll go right into that. So the problem I'll be talking about pretty much 80–90% of my talk is on simulating many-body Hamiltonians, and specifically I'll narrow it down to molecules, which is considered to be the most likely many-body problem to first show quantum advantage. So in this problem, we have interacting electrons, also interacting with ions, and we have all the Coulomb terms here in the kinetic term. And the standard thing we do is what people do also in chemistry, which is choose a basis. So there you don't only choose the basis, you also choose how many orbitals you're going to keep from that basis. And then you construct your Hamiltonian by computing these Coulomb integrals. So these H's here are classically pre-processed, and they're the part of the input to your quantum simulation problem. So this H is known. And then keep in mind that these A-dagger A's, these creation annihilation operators are fermionic, which means that they have to obey anti-commutational relations shown here. So to map fermions to qubits, you have to worry about that thing. We'll talk about that in a moment. But first, you have to decide what is your encoding. And the simplest thing you can do is take the number of qubits to equal the number of orbitals. And when I say orbitals here, I mean spin orbitals, so they can only have a single occupancy, or be unoccupied, of course. So there's this dual kind of nature to the orbital, in the sense that it can be either occupied or unoccupied. And there's the same dual sense in the qubits, that it can be in state 0 or state 1. So it's a very natural mapping to do, to map the unoccupied orbital onto the 0 state of a qubit, and the unoccupied orbital to the 0 state of a qubit, and the occupied to the 1 state of the qubit. And this means that each qubit represents a particular spin orbital. This is called the Jordan-Wigner mapping, but of course this is not all, because you also need to worry about the fact that you have these fermionic anti-commutation relations, which, if you see here an example, let's say I have this state here, and I want to apply the raising operator on the third qubit here, then I would need to worry, on the third orbital here, I would need to worry about the fact that the first one is occupied. So when I pass A3 through A1, I get a minus sign. And this is, of course, something that I need to preserve when I go to the qubit space. And to preserve that, what we do is we multiply the raising lowering operators on the qubits, which is given by this x minus iy in this case, by z's. So these are Pauli z operators acting on the qubits that are before that in the enumeration sense. So these types of experiments have been shown in early experiments from Google, IBM, and a few other groups. And these, you can see, these are very small molecules, but it was still, I think, inspiring kind of experiments to show that you can actually be in an era where you're starting to do some simulation, even if this is something you can do on your laptop still. So these are dissociation curves. It's the energy of the system, in this case, this hydrogen molecule, as a function of the interatomic distance, and they did a few kind of modest, small-sized molecules. So, of course, these were very nice experiments. They're useful to do because they help you learn better how to control your hardware. They help you constructing simulation algorithms and overcoming things like noise. But of course, they're still very, very small. And the question is, how do we scale to a larger number of qubits? So, of course, the main thing is we need better hardware. This goes without saying. The coherence times and gate fidelities need to be better. And that's something, of course, the community is working very hard for, and our center is working very hard for. But you can also, of course, do algorithmic improvements, which is another thing our center is trying to do. And this includes what kind of ansatz you use, how many measurements you need, etc. So my talk will focus on the second thing, and specifically on the question of the ansatz. So let's see what people are considering in terms of ansatz. So in these IBM experiments I showed you, they took the road of looking into what can their hardware do and go with that, which is a very natural thing to do. So there they parameterize all the single qubit gates and layers as shown here on the different qubits. And then there's an entangling piece shown in green over here, which does not contain any parameters. This can be C0 in the Google experiment, I'm sorry, in the IBM experiment. This was native interaction, so it was beyond just 2-qubit interactions. But anyway, there's some entangler over here, followed by another set of single qubit gates also parameterized. And then you can just keep going. So one issue with this, it's a very kind of ad hoc ansatz. There's no physical motivation for using it. But perhaps more importantly, it's inefficient in the sense that you're probably spanning too much of the Hilbert space, and there's nothing to guide you here with respect to where to search. And it's actually the type of ansatz that people have shown has barren plateaus. So there's optimization issues associated with it as well. The other very prevalent ansatz that's discussed in the literature is inspired from chemistry. And there you can basically take all the A-dagger A's and higher orders of these and exponentiate them to make unitaries. So here, if you combine appropriately A-dagger A terms shown with this t in the exponent, such that this operator, the resulting operator here is unitary, you can create this operator that is called the unitary coupled cluster. You could stop at second order, in which case it's called UCC-SD. SD stands for singles and doubles. And this is something, some variations of this are used in classical quantum chemistry, meaning quantum chemistry on classical computers. And that's kind of the reason this was imported in the quantum domain. On the other hand, this can also lead to very long circuits, and it's inconsistent with low-order tritorization. So you see here you have a very long string of operators in the exponent. To be able to translate those into your quantum processor, you need to break it up into individual exponentials that can be done on 1 or 2 qubits. And then you run into this issue of tritorization that I mentioned earlier in my talk. And if you stop at lower tritorization, which is what we can do right now and in the near future, then you have even more severe problems, which we have shown in this paper, where we showed that for some choices of lower tritorization, you can get very close to the ground state energy. For others, you cannot. So then there's an arbitrariness coming in from tritorization. And however, the biggest way I would kind of unify, the shortcomings of these two is that they're both generic. So no matter which problem you're solving, if you're solving a hydrogen molecule, or if you're solving beryllium hydride or some more complicated molecule, these tell you to use this ansatz no matter. So what we want to focus on is how can I have a better choice of an ansatz, and how can I specifically tailor it to the problem I'm solving. And we want to incorporate the following elements. We want to consider the fact that coherence is very precious. So we need to make shallow circuits. Classical optimization, on the other hand, is also not infinitely powerful. So we don't want to overburden the classical optimizer. And we would like to span the solution where the space where the solution lives. And this is what, in this review paper I showed, was called faithfulness, and we call exactness. So I'll tell you in the next remaining time how we propose to do this, our theoretical work on this. And you can separate the approaches we've introduced in 3 different categories. One is enforcing symmetries. The other one is the adapt VQE algorithm. And the third is a pulse level VQE, which I'll talk about in the end. So the features we want to have here are shallow circuits, small number of optimization parameters, and exactness. All right, so the first approach is preserving or enforcing symmetries. And you can think of this in the following way. Unlike what we usually think about in quantum computing, where we want to create some U, some unitary operator, here we have more modest goals. What we want is to create a specific state. And if you know something about that state, such as the symmetry sector in which it lives, then you can build that into your ansatz by building it into the circuit that creates that ansatz. So that's exactly what we want to do. And in a schematic here, this is the full Hilbert space. This is some symmetry subspace, and this is the ground state. So we want to only search within this S and not in the whole H. So we can start looking at different types of symmetries. The most obvious symmetry is number of electrons. So before we impose particle number, if we have n orbitals, we map those to n qubits, and we start search over the Hilbert space. Then we have 2 to the n or 2 to the n real parameters. However, if we know from the physical problem we're solving that there's only m electrons in this molecule, then we don't need to search all the space. We can search in a more efficient way by just searching on the order of n, choose m. What that means is that I can fix the number of occupied orbitals in the beginning by choosing the number of zeros and ones. And then I can apply gates that have the structure. So this is in the 0, 0, 0, 1, 1, 0, 1, 1 basis. And you see that here there's this middle part mixes the 0, 1 and the 1, 0. So if I use these building elements in my circuit, then I can create a circuit by having this structure. And we've proven that, at least we've showed with exhaustive numerics, that if I use a circuit that has the structure and I choose the number of these gates such that I saturate this number of parameters, then I can get any state I want with 100% fidelity. So this minimizes the number of optimization parameters. If you want to guarantee that you can get any state that has this number of occupied orbitals, then there's no better way you can do it in terms of number optimization parameters. And it's also hardware friendly because you see it only involves 2 neighboring qubits at a time. We've also, I should say here that this is just an example I'm showing you. We've done similar work for spin projection, total spin. And here, if you also want to impose time reversal, you can set the phi parameter to 0, and then you're reducing your optimization parameters by a factor of 2. We've also compared to ansatz that are built in the IBM hardware. And this red one is the one I showed you, and you can see that it performs very well in terms of minimizing the energy. And it also, by construction, has the smallest number of optimization parameters shown here. And this is what you would have from these other circuits. And in some cases, it also has a small number of C0s, even though this is not guaranteed. All right. So this is just giving you a flavor. There's much more in these 2 papers I linked. And this takes me to the second approach, which is the adapt VQE algorithm. And if you want to think about this kind of in a more global way, I introduced earlier ansatz that people are considering, the hardware efficient and the UCC. I would call these completely problem agnostic. They're the same no matter what you're simulating. Then you have these somewhat problem tailored predetermined ansatz like the symmetry enforcing ones, because here you know something, you know the symmetries of the system and you're enforcing them, but these are still predetermined ansatz, so they know a bit about the system, but they don't know a lot much. So then we want to go to this extreme end here, where I have problem tailored ansatz, which are also dynamically created. So I want to get information out of my quantum computer to help me build the ansatz. And you can view in the same schematic I showed you before. Here we start from some reference state, and the adapt algorithm basically gives you little steps that take you towards, hopefully in a straight line, in some sense, in the Hilbert space, toward the solution. So this algorithm has two main ingredients. One is the operator pool. So this is just which operators will potentially enter into your ansatz. And you can choose these in many different ways. I'll give you some examples. And what we do in this algorithm is we apply unitaries out of this pool, created out of this pool, one by one, each carrying an optimization parameter. And we apply that to some reference state we have picked. The second key ingredient is how do you decide which operator you append next. So you need to have some criterion, and we had, we have one we're using, but this is not necessarily the only one. The one we used in most of our work is take the gradient of the mean energy with respect to this theta. So you can imagine testing different operators out of your pool over here, and then this criteria would hopefully tell you which one would have the largest effect in changing the energy. And what's nice is that you can show that this left-hand side equals this, and this operator is a Hermitian operator, so this is another observable, and you can measure this on the hardware. So you can make measurements on the hardware that tell you which operator to use. And this is a schematic that's taken from our early paper. You initialize select operators from your pool, and you measure the gradient of each one of them with respect to the state at that given step. And then you choose the one that has the largest gradient, you append it. If this gradient is larger than some threshold, you append it. And then the ansatz now is grown by exactly one unitary. And you measure, you do a VQE. So now you re-optimize all the parameters that exist in this ansatz, including the new one you added. And then you just keep going and you add operators this way. Let me also note that you don't throw out operators from the pool. You always preserve them in the pool, so some can appear multiple times. Right, so the first thing we tried was taking operators that look like the ones in the UCC ansatz, so dagger A's and doubles, and creating their anti-Hermitian version because we want to exponentiate those. And here I'll show you some results. So in the x-axis, this is for 3 different molecules. These are classical simulations. We show the dissociation curves. So in the x-axis, I will have here I will always have the interatomic distance. In the case where there's more than one, I take them to be equal. And in the y-axis, we have the energy. In this scale, everything looks the same other than the mean field Hartree-Fock. So I'm going to show you here the error instead. So this is the error in logarithmic scale. And here you see the differences. So the orange one is this UCCSD, which is the exponentiation of the sum of different A dagger A's and A dagger AA with different coefficients in front of them, which are optimized. And the different colors here, the red, purple, and brown, show the 3 different thresholds we chose for the adapt algorithm. So we made this gradient be smaller than epsilon sub j. In each case, of course, as you make this epsilon smaller, you have better performance. And you see here that the more kind of tight versions of adapt do much better than UCCSD. But what's even more important is that they do better with much fewer optimization parameters. So here UCCSD, because it's a fixed ansatz, right? It's the same no matter where I am in the interatomic distance. I have the same number of parameters. And you see that what's the adapt algorithm tells you is that you don't need this many parameters. You can achieve chemical accuracy, which is this shaded area, with much fewer parameters. And in the one case where adapt needs more parameters, shown over here, is the case where actually UCCSD is not performing well. So it's, this seems to imply that you actually needed these extra parameters. All right, so here what am I comparing? I'm comparing exponentiating this sum of different single and double operators with a version where I apply them one at a time. So you could argue that this might be an artifact of the fact that I have effectively trotterized. And I want to show you that this is not the case, because you can take the UCCSD ansatz and trotterize it in many different ways. And this is what we've done here. And you get different types of behavior, which you can all kind of see are lumped together here. The dot here is the UCCSD. But you see that when you do the adapt algorithm, you get qualitatively much better convergence in curves that are very separated from these that bunch together. And this is something we did for a particular molecule at a bond distance that has strong correlations, but we've tried it for many different examples, and we always see this qualitative behavior. All right, so one issue, of course, is that I told you that trotterizing is something we don't want to do, and that I don't want to exponentiate operators that are when broken up into constituent single qubit gates become very long. So the way you choose your operator pool will determine how hardware friendly your algorithm will be, right? So if you want something that's very hardware friendly, you don't want to make these A's spread over the whole system, which is what the fermionic operators would do. So what we did next was we took more hardware efficient pool, where we took the Pauli strings to have up to 4 Pauli. So I'm only touching 4 Paulis, 4 qubits at a time, not, I threw away all these Z strings that would come naturally from translating fermionic operators into qubit operators. And we compare here the previous result, the fermionic case, with this, what we call qubit adapt, this other pool. Qubit adapt is something more general. It's any pool that would you would choose other than fermionic that's more hardware friendly. This is just a somewhat arbitrary choice. So what you see here, so this is the original, the fermionic case I showed you before. Here you have fewer parameters. So this adapt iteration number means how many operators am I appending to get convergence. And you see here that the fermionic one appears to do better. And that's not surprising because I'm lumping multi-qubit things with one parameter in the exponent. So it's not surprising that I would have fewer optimization parameters. On the other hand, if I now compare number of C nodes, you see that the hardware efficient pool qubit adapt does much better because these operators it's using as its building blocks touch fewer qubits at a time. So overall, since the quantum resources are more precious at this point, you want to minimize C nodes rather than optimization parameters. But there's many other choices of pool, and there's been follow-up papers to our work that show you can do even better in terms of doing, compared to fermionic adapt. So one important question is, how do you choose this pool? One way you can choose it is just put in there all the gates that are easy to do on your hardware, but then you need to worry about, are those enough? And will I get convergence? So we have examined this question in some depth, and we introduced the idea of complete pools, which means pools that contain all the necessary operators in order to, in principle, reach any state in the Hilbert space. And I should qualify this, we limited ourselves to real states because we're assuming time reversal. So what we're doing here is we're taking the operators from the pool, which are A's, and we're taking their commutators with those. We create the full algebra here, and we create the set B over here. So the statement is that we have a complete pool if from any arbitrary state get into any other state by applying these B sub i's. And I'll show you some numerics that support this. We took complete versus incomplete pools. We just took some random Hamiltonians, and we showed that with the complete pools, we can always get convergence, whereas with incomplete, sometimes we didn't. And if you want to run this on hardware, you have to worry about how big are these complete pools. They better not be, exponentially large, so that I can actually hope to do this on my hardware. And what is nice is that we showed that the minimal size of complete pools is linear in the number of qubits, and the scaling is 2n-2. So long as I have the right set of 2n-2 operators, then I can go from any real reference state to any other real reference state. And we have two concrete examples in this paper that actually was published yesterday, where we show two different examples of minimal complete pools shown over here. And in one case, you see the operator only touches 2 qubits at a time. So this seems to be quite hardware friendly. I also would like to make a comment here that adapt VQE, the structure of this algorithm is a little bit reminiscent of this paper I showed you of trainability and how to overcome barren plateaus, in the sense that because you're growing the ansatz dynamically and you're optimizing the parameters on the way, the new set of operators will see the optimized parameters already. So we have reason to believe that adapt naturally behaves better and is resistant to barren plateaus, these optimization issues. We have some unpublished work, this is a work in progress, where we examine this question in more depth. All right, the last approach for fermionic problems that I'll tell you about is control VQE. And this is, this work came out of the realization that even these dynamical adaptive approaches might still be demanding for hardware. So the question is, can we do something that's even more hardware friendly? And the idea here is, instead of parameterizing the circuit, parameterize the pulse directly. So here we're throwing out the circuit, we're parameterizing our pulses, and otherwise we're doing exactly the same as we do in VQE. We measure the mean value of the energy, we optimize classically, and we repeat until it's converged. So this is just a schematic of how this works. I can parameterize my pulse in many different ways. We did an example where we took Transmon qubits. And the part we parameterized was the single qubit drive. And we also fixed the frequency. So we only optimized amplitudes to make this more experimentally friendly, because we didn't want to have to switch the frequency of the drive during the pulse. So I'll show you a schematic of how one of the algorithms we have in the paper works. So we start with square pulses on all the qubits, and then we chop the square randomly in some point, and we optimize the two pieces separately. So now I get some new pulse for each qubit. I should say that I'm assuming always on interactions similar to the IBM hardware. And then I'm taking the remaining piece, the largest of the two pieces, and I'm chopping that. I'm re-optimizing, and I get something else. And then you can keep going. So we have some example, again, classical simulations. This is a dissociation curve for hydrogen 2. And basically, this demonstrates that we can find the exact solution with this approach. And in this example, we show for a few different molecules that as I increase the number of pulse segments, I go monotonically toward the ground state. So I'm reducing and reducing further the energy error. And then if you do a rough comparison between doing this and doing gates for a similar type of, to create the same unitary that the pulse creates, I would need many orders of magnitude more coherence time. Okay, there's also an interesting paper, Perspective and PRX Quantum, that I'm showing here, that talks about the interplay of quantum control and VQs. All right, so this takes me to the very last few slides of my talk, and I'm switching topic a little bit to talk about optimization. This might sound like a very different topic, but in fact, it's very much related, because here the only difference is that instead of looking for ground states of many body Hamiltonians that occur in chemistry and solid state physics, I'm looking at Ising Hamiltonians. So these are much simpler Hamiltonians in the sense that they're diagonal. So this is a combinatorics problem to find which combination of up and down spins would give me the ground state energy. And this is actually combinatoric optimization problems can be mapped to Ising problems. In this case, this is the max cut problem where I want to cut the maximum number of edges. And then I'm coloring the spins or the nodes that end up on a different side of these of this cut, and I'm calling that spin up or down. depending on the color. So this is something that famously is addressed by the QAOA, which is an algorithm inspired by the adiabatic theorem, where you start with a reference state where all the qubits are in state plus. And of course, this is an eigenstate of a Hamiltonian that is the sum on the X Pauli of each qubit. And the QAOA has a fixed ansatz structure, which is, however, it can be grown in the sense that I can add more layers. So it has a sense of a depth, but it looks the same at every layer. So you're acting the problem Hamiltonian, which is just this Ising Hamiltonian over here, with some coefficient gamma 1. Then you're acting this so-called mixer Hamiltonian, which is the sum of the x's that are single qubit gates. And then you're repeating with this Hamiltonian, etc. And you are changing, you're allowing the algorithm to pick different parameters for each layer. So there's a vector of gammas and a vector of betas. And then you want to minimize this quantity, which is very much analogous to minimizing the cost function I showed you in the chemistry problems. So what we are looking at in our work is looking at this mixer and asking, can I make other choices which are hopefully better than what this original algorithm suggests? And let me point out here that this choice was somewhat motivated physically, because if you view this like an adiabatic problem, what you're doing is starting from the eigenstate of this Hamiltonian B. And in a real adiabatic problem, you would slowly vary some parameter and tune B into C. So you could view the QAOA ansatz as a trotterized version of this adiabatic problem. Of course, we again run into this issue that finite order trotterization might be really different than what you would expect from infinite order trotterization. So what we suggest to do is to preserve this QAOA structure, which alternates the problem Hamiltonian with some mixer, but give more flexibility to how you choose the mixer. So instead of having this sum of x's, just allow use of more general operators here, which could be consistent, which would ideally be consistent with your hardware. So we define mixer pools similar to our adapt pools, and then we use adapt strategy to determine which mixers to choose next. And we've done simulations for 2 different types of mixer pools. One is just using single qubit gates, so giving ourselves a little bit more flexibility than just rotating all qubits by the same amount and by our own x. So here we rotate about other angles and other axes. And you can give yourself a little bit more flexibility by throwing in entangling gates into your pool. So these are just 2 qubit entangling gates. And we've shown that you can do much better if you allow yourself to make these changes to QAOA. So here I'm comparing as a function of layer number. I'm looking at the energy, and I want to minimize this for 2 different types of the max cut problem on 2 different types of weighted graphs. And you see that with if I allow entangling mixers, I can get much faster convergence compared to the original QAOA and just doing single qubit gates. And what you could ask here is at what expense, right? Of course, the intuition usually is that more entanglement is better, but that's not what we find. So if I look for a particular value of the energy here, you see I need fewer gates for the adapt version of QAOA with entangling mixers, but I'm also using fewer C naughts. So here, if you look at the number of C naughts, which is the pink bar here, the multi-qubit mixers actually counterintuitively uses much fewer both parameters and C naught. So what this tells you is that the original QAOA is consuming more entanglement without gaining anything out of it. And similar conclusions hold for this other graph. All right, so this takes me to basically my last slide. We're now examining a lot of the mathematical features of the adapt algorithm, such as the pool, growing criterion, etc. There's a connection between QAOA, adapt QAOA, and shortcuts to adiabaticity, which is very interesting and I didn't have time to talk about. You can find in our paper. And we're wondering if there's deeper connections between adapt and the concept of shortcuts to adiabaticity. And then I made these in bold because they're probably most relevant to our center, looking into control VQE for particular type of hardware, incorporating hardware features and constraints in our algorithms, and then finally simulating dynamics with adapt. There was a nice paper also from our center using ideas from adapt VQE to solve dynamic problems. All right, so this takes me to my summary. I introduced the idea of variational quantum algorithms. I talked about how to make problem-tailored ansatz for VQAs, and specifically 3 different approaches, and also touched upon our optimization algorithm adapt VQA.
Excellent. Thank you very much to Sophia for this wonderful talk. So we have a couple of quick questions, or let's see, Diana, are we able to take questions? We're cutting a little close for time. So the first question that we have on the chat is, what is a typical, this is from John Orell, what is a typical circuit depth that is the number of gates in one cycle of a VQE step? This was sort of earlier in the, so this was about midway through the talk.
Number of gates. So this depends a lot. Let me see if I have anything. It will depend a lot on what kind of ansatz you use. In our simulations here, you could see that for these types of, these are more strongly correlated. I don't know if you can still see my screen. These more strongly correlated molecules like the hydrogens, you would need about something like 20 something to start reaching good values, maybe 20. For less strongly correlated molecules, you probably would need fewer than 10 or even fewer if you pick your gates well and you pick the order well. So it's very system dependent, but the general trend is that, of course, more strongly correlated molecules would require more gates.
Great. Does that answer John's question? He's not speaking up, so I assume so. So we also have a question from Alicia Siddiqui. What is an example of a particle preserving gate?
Yes, so let me show you here. Maybe this question was asked before showing this. So this is one example. So here the basis is 0, 0, 0, 1, 1, 0, 1, 1. And you see that the 0, 0 state and the 1, 1 state don't mix with anything, whereas the 0, 1 and the 1, 0 mix. So this means that I can create superpositions of 0, 1 and 1, 0 without leaving this subspace if the subspace was already occupied. And then by stacking them in this way, you can grow this to a larger number, but this is your building block.
Great.
Peter, yeah, let's just ask one more question.
Okay, one last question from John Orell again. Can it be demonstrated that VQE circuit depth can be tailored to the error rate present in the quantum hardware?
Tailored. What do you mean tailored? Maybe I'm not quite understanding the question.
I guess I'll ask John to speak up.
Yeah, thanks. It's just a question of if you have a higher error rate, can you selectively pick your circuit depth to be smaller or take advantage of low error rates by having longer circuit depth?
Oh, I see. Yes. Yes, you can do that. You can also, I mean, with this adaptive approaches, it's kind of a natural thing to do. You could also, if you know where the error comes from, you could select gates that are not as prone to error and use those in your operator pool. And maybe in that case, you would not, use operators which induce more error. So that's something we're interested in, which is also an interesting question relating to hardware in our center. How can you take features of the hardware into account when you design these algorithms?
Thank you. Very nice presentation.
Yeah.
Thank you.
Yeah, let's thank Sophia one more time for this wonderful presentation.
Thank you. Thanks, Peter.
Right.
Yes, thank you very much, Sophia. We really appreciate it. And thank you, everybody, for joining today's Quantum Thursday. We will have one more in the series next Thursday. So look forward to seeing you then at the same time and the same Zoom link. So thank you very much.